Welcome to this lecture on positron emission tomography, understanding the physics and radionuclide production with PET imaging. Here are the objectives for this presentation. To recall nuclear physics as it relates to positron decay, recall that positron decay occurs in a neutron-deficient nucleus. The proton becomes a neutron. The excess energy and charge are released as a positively charged electron, also known as a positron, and a neutrino. The positron has the same mass and characteristics as an electron, but it carries that positive charge away from the nucleus. Isotopes and radionuclides that decay by positron will maintain their atomic mass. It will stay the same, but the atomic number will decrease by 1 because the number of protons in the nucleus is decreasing by 1. This is done for maintaining the conservation of the mass number and the charge. With positron decay, there's always a secondary annihilation reaction. The positron carries the positive charge and is thus attracted to an electron. Eventually, a positron and an electron will collide with each other and they will annihilate. In other words, all of their mass is converted to energy and released in the form of a photon. So the mass of a positron or annihilation reaction is completely converted into energy. And this is released in the form of two 511 keV photons, also known as annihilation photons. This is an example of beta decay or beta positive decay, also known as positron decay. Notice in this example, the nucleus is neutron deficient. It has 4 protons and 3 neutrons. In turn, one of those neutrons will turn into one of the protons will turn into a neutron, and a positron or positively charged electron is released. This is another example demonstrating the beta positive or positron decay and the subsequent annihilation reaction. The unstable parent is neutron deficient. One of the protons turns into a neutron. You have the release of the subatomic particle there, and then also the release of the positron. So this is the neutrino right here, and then the positron. Notice that that positron doesn't necessarily follow in a straight line. It is positively charged, so it has a magnetic field. But it is attracted to an electron. They are the same mass, very similar characteristics, but one is a positive and one is a negative charge. So they're highly attracted to each other because of, opposites attract. And so when they collide, all of their mass is converted to energy in the form of these two 511 keV gamma photons, and those will be emitted in opposite directions of each other. This is the schematic display, decay scheme of positron decay, or beta positive as it's also called. So you have your parent. It's always going to decay down into the left, because if you look at the periodic table as you go across a row, it will increase in the number of protons. And with this decay, you're losing a proton. So that's why the atomic mass stays the same, is because that proton gets converted to a neutron. So the atomic mass stays the same, but the number of protons in the nucleus will decrease by 1. When it does that, remember that the number of protons actually kind of dictates what element it is and its chemical behavior. So as it becomes, as it loses a proton in the nucleus, it actually becomes the element directly to the left of it on the periodic table. So it will decrease by 1 in the daughter, and so the decay scheme will go down and to the left. And this is a summary of all the radioactive decay that is involved in nuclear medicine. Of course, the X-rays that are involved with CT for hybrid imaging are not on this graph, but all the other types of decay you see in nuclear medicine are. So just as a quick summary, alpha decay basically happens with really, really heavy atoms, and the nucleus essentially sheds the equivalent of a helium nucleus off of it. You have 2 protons and 2 neutrons that are attached together. So the atomic mass in that one will decrease by 4, but the number of protons decreases by 2 because it's only losing 2 protons. So that will become the element 2 to the left of it on the periodic table. The next one is beta decay or beta negative decay. With this one, it essentially sheds an electron from the nucleus. The atomic mass is unchanged, but the number of protons in the nucleus will increase by 1. So the daughter actually becomes the element to the right of it on the periodic table. Beta decay is seen in mostly therapies. There are some beta negative decay radionuclides that are also used in imaging, and that's usually because when something undergoes beta, it is still unstable, and it usually will emit a gamma ray with it. So the radionuclides that are beta negative that have a good energy of gamma that comes off of it also can be used for imaging, and an example of that one would be I-131. Gamma decay is what we use most of the time when we're looking. Gamma and electron capture down there at the bottom are the ones that are mostly used in imaging in general nuclear medicine. With gamma decay, also known as the metastable, the nucleus is just in a really excited state, and it releases some of that excess energy in the form of a gamma ray. And so that's what we use a lot of time in imaging. That's what 99M technetium is. Those radionuclides will be metastable, where they have excess energy, and so they will be denoted with an M when you write them, like 99M technetium is. For those ones, because they're not changing the atomic mass at all, the protons are staying the same, it's just a release of energy, they remain the same element. The atomic mass and the number of protons remains unchanged. With positron decay, like I explained on previous slides, you have a neutron deficient nucleus, and so the neutron is turning into a proton, and it's releasing a positively charged electron or positron particle from the nucleus. So with electron capture, which is the last one, it's actually capturing an electron, exactly what it sounds like. It's capturing that electron. Electron capture is the alternative to positron emission. So this is also an atom that has a neutron deficient nucleus. And so basically what it will do is it will capture an electron. That electron forms with a proton and becomes a neutron because the forces kind of neutralize. But that requires a lot of energy. There will be excess energy in the nucleus. It releases that in the form of an X-ray, and you have some gamma emission that can come along with that with electron capture. So atoms that have a little bit more energy tend to decay by positron, and then if they don't quite have enough energy in the nucleus for a neutron to convert or for a proton to convert, then they will decay by electron capture. So what we're doing with PET imaging is we are detecting those coincidence or annihilation photons. So after positron decay and negative, so after the positron and the negatively charged electron undergo that annihilation reaction, those two 511 keV are emitted in 180 degrees from each other. And that's what we're detecting with positron emission. We're detecting those two 511 keV photons that are opposite of each other. This is called coincidence detection. Those photons will occur a few tenths of a millimeter from the origin. So this is one of the reasons that spatial resolution is really good in PET imaging, but it's never going to be perfect. That positron will travel a little bit from the original nucleus and that original atom before it collides with an electron. And so even though it only travels typically a few tenths of a millimeter from the origin, different positron radionuclides will travel. Some of them don't travel as far before they annihilate. Some of them don't. Some of them travel a little further. And so the spatial resolution will be slightly different for different PET radionuclides because it will travel a little bit before it annihilates, and we can only see the annihilation photons. We cannot see the original origin of the positron. With ACD, or annihilation coincidence detection, the near simultaneous detection of the two photons is used to localize their estimated point of origin. So this is an important point to remember when we are imaging with PET, is we're seeing the location of the 511 keV photons, not from the original positron decay. Time of flight is an important concept to keep in mind with PET imaging. In theory, it is possible to determine the localization or the location of the event by determining the time distance between the photons. So we're looking at the location of the annihilation event, not the location of the positron. But it is possible theoretically to determine the location of the annihilation event by determining the time difference between when those two photons hit detectors opposite of them on the PET scanner. This allows for tomographic reconstruction without a lot of heavy mathematical algorithms, and it achieves timing accuracy down to the picosecond. Sometimes this will lead to increased signal to noise ratio in the images, but with modern technology, it is improving greatly. Although spatial resolution is improved with PET over general nuclear medicine, there are quite a few things that can influence the spatial resolution. Like I said, the element with positron decay and how much energy that initial positron has will influence how far it travels before it annihilates. That will degrade the spatial resolution with PET imaging. But the spatial resolution is largely determined by the size of the detector elements and the internal resolution of the PET scanner. This greatly differs from SPECT and general nuclear medicine, which is also reliant on collimation. With PET imaging, we're not reliant on that collimation. There are a few degrading factors to spatial resolution. As mentioned, that positron range. This is an important term, the effective positron range. That's the average distance from the emitting nucleus to the end of the positron range. That's essentially how far that positron particle traveled before it annihilated and produced those 511 keV photons. So the further that positron travels, the less spatial resolution we have. So it's a little bit of an inverse relationship there. And then non-collinearity is also an important term to remember with PET. The annihilation photons almost never are emitted at exactly 180 degrees from each other. We say that theoretically they are, but it's almost impossible for them to be exactly 180 degrees. And so what that means is when that time of flight traces that location back to where it thinks the positron annihilated, it's not going to be exactly in the right spot, especially if it, gets photons that are slightly off or a little bit off from 180 degrees from each other. Then that's going to kind of make it not as accurate to the location of where it occurred. And this is an example here of the annihilation event and the blurring that will be caused by the effective positron range. So in this image here in the top left, you have the nucleus of a positron emitting radionuclide. And then as that positron travels, we would expect it to go kind of in a straight line and annihilate right here at this location. But instead, it actually followed a little bit of a wonky path here before it collided down here with an electron and had that annihilation event. And then also, the two 511 keVs are not exactly 180 degrees from each other. So as the scanner tries to trace that back, you're going to get even further away from where that positron radionuclide actually is located. Positron range and non-collinearity create barriers for improving the spatial resolution of PET systems that cannot be overcome simply by using smaller detector elements. This just has to do with the physics of the radionuclide, and so we can't image that positron at all. We can only image the annihilation event, and so we are forever restricted to where that annihilation event occurred. Now we're going to talk a little bit about the production of radionuclides for PET. So regulation of PET radiopharmaceuticals is overseen by a couple different institutions. The Nuclear Regulatory Commission regulates cyclotron-produced radionuclides, and the FDA also oversees the production and manufacturing of radiopharmaceuticals. All PET radiopharmaceuticals that are approved by the FDA must be manufactured in compliance with good manufacturing practices. The Code of Federal Regulations, 21 CFR Part 212, specifically addresses the production of PET radiopharmaceuticals. And then the United States Pharmacopoeia, they're not necessarily a regulating body, they're more of a guidance that they provide. However, most pharmacies and pharmaceutical entities do adopt the guidelines of the United States Pharmacopoeia, and so their guidelines and recommendations end up becoming regulated. So the ones that the USP covers are F18, ammonia, O15 water, and F18 fluordopa. PET radiopharmaceuticals are either produced by a generator or a cyclotron. Most of the radiopharmaceuticals that we use in nuclear medicine that are PET-based are produced by a cyclotron. However, there are a couple generators that are out there, two, one for rubidium and one for gallium-68. And generators are typically on site. Now, the gallium-68 generators tend to be more located at a local radio pharmacy, whereas the rubidium generators are right in the scanner room. Cyclotrons are typically off-site at large-scale nuclear pharmacies. Cyclotrons are very large. They take up a lot of space. And so if you are at a very large institution, very large research hospital, then you may have a cyclotron on site, but for most of the United States, for most places, that cyclotron is off-site at a larger scale nuclear pharmacy. So as I stated, there are two generators, the rubidium-82 generator. Rubidium-82 is a potassium analog and is used for myocardial perfusion imaging. And then the gallium-68 generator. Gallium-68 does readily tag to a lot of things, but what we know it as is mostly being tagged to PSMA for prostate cancer imaging, or to dotatate or dotatalk for neuroendocrine imaging. So rubidium-82 is the daughter of strontium-82. Strontium-82 has a half-life of 25 days, but rubidium-82 has a half-life of 75 seconds. This is one of the reasons that it's important the generator is in the scanning room for this one. This is one of the reasons why, and that elution will occur and go straight to the patient. And essentially by the time that the patient is done with the study, almost all of that radionuclide has been decayed. Elutions have to be performed bedside due to the short half-life, and the generator is eluted with saline and injected directly to the patient. These generators need to be replaced about monthly. Some of them will go up to 6 weeks. However, the elution starts to really get watered down by the end of that 5 to 6 week mark. So the rubidium-82 generator contains switches and detectors that monitor the dose being delivered to the patient, and it turns off once the desired activity has been ejected. The generator will recover in about 10 minutes and can then be eluted again. This is a really rough design of the rubidium generator. It will come on a cart like this. There are two major companies that make these carts. They look very similar. The modern ones will actually have a computer screen on top and they're computer operated. But basically the saline goes in, it washes over that column that has rubidium and strontium in it, and then it gets measured within the instrument, and there's a little three-way valve. When you're doing QC or whatever, that waste will go into a shielded container that has to be decayed and then thrown away, and then the patient dose will actually go straight to the patient. Rubidium-82 generators are used for myocardial perfusion imaging. The rest dose is injected first. This is not like a general nuclear cardiology stress test with SPECT where you can do 2-day or you can do stress first or anything like that. There's not as much variability there. The rest dose is always injected first. Imaging begins 90 to 120 seconds later, lasts for about 5 to 7 minutes, and then the stress dose and the pharmacologic agent are injected. Patient remains on the scanner the entire time in the same position, and patients will receive anywhere from 30 to 60 millicuries per injection. So these are the two commercially available generators. On the left is the RubyFill generator that's produced by Jubilant, and on the right is the Bracco generator that is, or the Cardiogen generator that is produced by Bracco. Both of them require that saline that are on there. Both of them have a computer touchscreen where you control the elution and the patient information. And then for both of them, this bulkier part of the cart is where the generator actually resides. So this is an example showing the Cardiogen generator being kind of installed and changed out. There's a lot of different tubing and that needs to be put in the right places. This first one here, assembly package, is where it hooks to the saline. And then it has syringes here that go inside of it. And then it has the patient admin kit where it actually will put the dose to the patient. So that patient admin set is what's hooked up to the patient. So this is another example that saline will wash over that, go through the peristaltic pump. There's a pressure sensor to make sure that the pressure is where it needs to be. And then it will go straight through the column for the strontium and rubidium. The strontium theoretically should stay in the column and the rubidium-82 washes away with the saline. It is counted. There is a small scintillation detector within that cart. And then if they're wasting it, goes to the waste bottle. If they're not wasting it, then it will go through the patient infusion line and go to the patient's heart that way. There is some important quality control that needs to be considered with the rubidium generators. First is the radionuclide purity. It has to be assessed for breakthrough of strontium-82 and also strontium-85, which the strontium-82 decays to. The first elution of the day is discarded and the second elution is tested prior to the first patient. And then using the dose calibrator, measure and record the rubidium activity and note the time. Allow at least 1 hour to complete decay and then measure the residual activity in microcuries of strontium-82 using the dose calibrator and the strontium-82 setting. Modern systems do allow you to do that within just a couple of minutes by timing it and looking at how much of the rubidium has decayed. The saline volume is an important thing to keep track of with the generators. It does have a maximum amount of saline that can be put through the column. And so that total volume of the saline needs to be maintained. And you will have problems with breakthrough and things like that if too much saline is used. The total volume of saline that passed through the generator column and levels of strontium-82 and 85 are continually tracked. And then there are alert limits set for the technologist, and this will initiate action if the limits are met. And that could either be the breakthrough of the strontium or it could be the total volume that's been eluted through the generator. These are the alert levels. If any one of these alert levels are reached, then the technologist must perform additional daily QC and tests after every patient. The first one is 14 liters of cumulative eluate volume that has been reached. That indicates that it's approaching the maximum amount of saline that can be used for that generator. And so additional quality control is needed to make sure that not too much strontium is coming through to the patient. And then the strontium-82 and 85 limits. For strontium-82, the level, if it reaches 0.002 microcuries of strontium-82 per millicurie of rubidium, or 0.02 microcuries of strontium-85 per millicurie of rubidium. And then the hard rule for stopping use immediately is if 17 liters of saline have been washed over the column. It's been 42 days post calibration, or the strontium-82 levels reach 0.01 microcuries of strontium-82 per millicurie of rubidium, or 0.1 microcuries of strontium-85 per millicurie of rubidium. If any of those four conditions are met, then the generator, you must stop using the generator. Now the next generator is the germanium-68 and gallium-68 generators. So germanium is the parent nuclide, that germanium-68 with a half-life of 271 days. This decays by electron capture and is sometimes used in quality control. The daughter radionuclide is gallium-68, which decays by positron. It has a half-life of 68 minutes, and it decays to stable zinc-68. A single generator can be used for up to a year, and it contains about 50 to 100 millicuries of germanium-68. It can be eluted hourly, and it has similar generator and tagging principles to 99M technetium, which makes it very favorable for PET imaging. Now, with the gallium generators, the elutions are not injected directly to the patient. They're labeled with large complex molecules such as peptides, and so there's a little bit more manipulation that needs done to produce the radionuclide, and so it ends up being made as a cold kit, similar to the way we make other radionuclides in general nuclear medicine. The impurity there is that it must be less than 0.001% of germanium, and there are trace amounts of some toxic metals that can come through, so those levels need tested also, and those are tin, arsenic, nickel, manganese, and aluminum. The chemical purity, it needs examined to limit the amount of iron and zinc to about 10 micrograms per gigabecquerel of gallium. And there is a cartridge method that is used to remove those heavier metals. And the radionuclide purity is less than 0.001% of germanium 68 within the sample of gallium. And this is tested using radiopharmaceutical purity with instant thin layer chromatography. These are some of the commercially available generators for gallium-68. Each one of them shows the eluent, the limit of germanium breakthrough, the volume that's eluted, chemical impurities that exist, and then, of course, the weight. So this is another image here of the gallium-68 generator along with the schematic drawing showing how it gets eluted. And this is very similar to the generator that we see for technetium. Of course, it is vented for pressure, maintaining the pressure within it. This one is eluted though with hydrochloric acid. That hydrochloric acid is washed over the column with germanium-68, and the gallium-68 is washed through along with the hydrochloric acid while the germanium stays in the column. The whole thing is lead shielded. It has a 0.22 micron membrane filter, and that's to make sure that no heavy things come through, no heavy metals, no microbes or anything like that can come through into the eluate. This is an evacuated vial. That's what kind of sucks that hydrochloric acid over the column and through the generator into that collection vial. And then the radio labeling methods, it will be supplied in little cold kits like this with all the necessary reagents to either make the DOTA somatostatin analogs for neuroendocrine imaging or PSMA 11 for prostate cancer imaging. And this is this device here is what allows you to kind of help tag those radionuclides. So the use of gallium-68 for PET imaging, the somatostatin analogs look for neuroendocrine tumors. The gallium-68 PSMA agents will look for prostate cancer, and then not available in the US, but there's also Galagas, which is used to image the lungs. So those are the two generator types. All the other PET radionuclides that are commercially available are produced in a cyclotron. And this is an image of a GE cyclotron here. And we'll talk about this a little bit in the next couple of slides. But this is showing you kind of the insides of the cyclotron. So PET cyclotrons are used to bombard atoms with protons or deuterons. A deuteron is a proton plus a neutron, and this creates a proton-rich radionuclide that will then decay by emitting positrons. So if it's proton-rich, it's neutron deficient, and so that forces it to decay by positron. And so essentially what we're doing with a cyclotron is just bombarding those atoms with protons so that the nucleus does become proton rich and will then decay by positron. Most common type is a negative ion cyclotron, In this type, it accelerates a hydrogen atom that contains an additional electron. This creates a negatively charged atom because it's a proton plus 2 electrons, and it accelerates those negatively charged atoms to a really high energy and then bombards the target. So this is the kind of a side schematic of the cyclotron. You have two electromagnets here on the opposite ends of each other, and then inside is where it accelerates to a high rate of speed. So the older positive ion cyclotrons will accelerate protons, deuterons, tritium, which is 1 proton and 2 neutrons, or alpha particles, which are 2 neutrons and 2 protons. Newer cyclotrons are almost all negative ion cyclotrons, where you have 1 positron and 2 electrons. This is sometimes called positronium as an element. And essentially it is stored right here in the middle. That's the particle source. And then with the use of these electromagnetics oscillating their charges, because it's a charged particle, it's going to get drawn one way or the other. So they oscillate their positive and negative charges to keep it spinning. And as it's attracted to those different poles, and those poles are changing, it will get faster and faster and faster, and it just kind of spirals in this trajectory until it gets to its maximum speed. And then each time that it passes this narrow gap here, it increases in speed. And so it'll increase as it's spiraling, and then eventually it will be directed straight towards the target. And at the target is where it bombards that nucleus and changes whatever is in this target here to something that will decay by positron. The whole thing is located within a vacuum that helps to control that reaction that occurs. So cyclotrons have a large vacuum chamber that sits between two large flat magnets. The negatively charged atoms are released at the ion source in the center of the cyclotron, and alternatively pulled and pushed by the electrodes, and these are called the Ds, but they will change in their polarity, and so there's a constant pull or push on that source ion, and so that is what increases the speed. So it will continually gain energy as it continues to have that outward spiral. Once the charged atoms reach a high energy and at their maximum diameter, they collide with carbon extractant foils, which remove those orbital electrons. Only that proton then comes through and bombards the target. So the positively charged particle beam moves in the opposite direction in the magnetic field to curve out the magnetic field and strike the target. And this is an example of what I just showed here. You have the ion source here in the middle, and these are the two Ds on each side. They're actually shaped like a D and then, backwards D. And this is the gap here in the middle. So as these Ds will kind of change their polarity, and this is a charged particle, it gets attracted, repelled, attracted, repelled, attracted, repelled, and that's what keeps it in that spiral trajectory. Every time it passes this gap here in the center, it gains speed and energy, and so it just keeps doing that in its spiral trajectory until eventually it goes through that um, kind of foil paper, and it will hold the electrons back and only allow the proton beam to come through. We call it a beam because it's essentially a stream of protons, and they will bombard that target. The target nucleus will take on those protons and become proton rich, which forces them to become unstable and then decay by positron. A lot of times there's something very simple here used in the target, like stable water. And so as it bombards that with protons, then it becomes proton rich. So particles are generated in bursts by the ion source. A high frequency AC voltage is applied across the Ds. The particles are injected into the gap, and that's where the ion source is. And then, like I said on the last slide, they're accelerated towards one of the Ds by the electrical field. Particles are in a magnetic field and followed a curved circular path around the opposite D, and the particles are accelerated across the gap. So every time they go over that gap in the middle, they gain about 30 keV of energy in doing so. And so they just continue on that outward spiral path within the opposite D. And each time they cross that gap, they gain more energy and they continue that outward spiral until they reach their maximum speed and maximum kind of outward outward spiral. And then the particles will be directed at the target. The beam is extracted from the cyclotron and directed towards that external target. There are a couple advantages of negative ion cyclotrons, which are some of the reasons why almost all the modern cyclotrons are a negative ion for our use. The negative ions will cause much less nuclear activation of the cyclotron and the surroundings than a positive ion cyclotron will. The negative ion cyclotrons are able to self-focus the beam towards the target, and then negative ion cyclotrons can irradiate two targets at the same time. So this is typically what's used in the production of F-18. The target element is basically just stable water, and then the protons, deuterons, and alpha particles are included. The particles must have a very high energy of 10 to 20 MeV to penetrate the repulsive Coulomb forces that are surrounding the nucleus. So all that's saying is it really has to have enough energy to overcome uh, the forces that are there in the stable atom, like the binding energy and the weak and strong forces within the nucleus, has to overcome that. And then once it does, it turns into fluorine 18, which is decays by positron. This is just a video that kind of helps understand the overall process.
This, you're about to witness a birth. Take a hydrogen molecule, now subject it to a strong electric arc, and there you have it. May I introduce you to Mr. Iron? This chap is a negatively charged hydrogen ion, so technically he is a proton nucleus with 2 electrons. Apply an electric field to him between the 2 D plates, watch him accelerate. See? Above the Ds he accelerates in a straight line. The magnetic field above the electromagnet supplies a centripetal force. This curves his trajectory and sends Mr. Iron back into the acceleration. IBA cyclotrons have 4 acceleration zones, 4 zones of magnetic field. This creates very compact high-energy cyclotrons with low losses.
An 18-minute cycle line accelerates up to 18 megaelectron volts.
The stripper removes the electrons and Mr. Iron becomes a single positively charged proton, and his trajectory changes. Straight into the near target where oxygen 18 is waiting. He crashes right into it. The energy level converts O18 into fluorine 18 through the PN reaction, releasing a neutron in the process.
So these are some of the advantages of the negative ion cyclotron. They have less nuclear activation. Negative ion cyclotrons are able to self-focus the beam, and then they can irradiate two targets at the same time. These are the radionuclides used in PET-CT imaging that are produced by medical cyclotrons. Carbon-11 is not as widely used, and that's partially because it has a short half-life of about 20 minutes. Nitrogen-13 is used for cardiac imaging, and that one is also very difficult because it has a 9.9 or roughly about 10-minute half-life. So for both of those radionuclides, as well as the next one, oxygen-15 with a half-life of 2 minutes, it really is important that that cyclotron be very close by. And so those are kind of restricted for the most part to places that have a cyclotron on site that's very close by. F18 is the one that's most widely used. This one has a half-life of 109 minutes, which makes it fairly able to be produced and shipped. And then gallium-68 is a little bit tougher. It's important to have a cyclotron close by. I do have a star by that one because, as you recall from just a couple slides ago, gallium-68 also has a generator. So gallium-68 is unique in that it can be cyclotron produced or it can be produced in that generator. Most of the time, because of the 68-minute half-life is still pretty short if you're trying to produce it and ship it somewhere. It's easier to have a generator on site. And then the copper 64 is another one. That one has a much longer half-life, and that one makes it a little bit easier for and more feasible for production and shipment. So cyclotron targets contain the material to be irradiated. Targets are typically liquid or gas. They must be adequately cooled to remove heat and must be kept under high pressure. The target material is pushed in and out of the target without physical handling. So this is used for F18 production. The target material is O18 enriched water. The water is pumped into the target, held during the irradiation at high pressure to keep it from boiling, and then pumped out of the target into synthesis modules for labeling. Those synthesis modules are essentially machines that enable it to be readily and more easily tagged without a radio pharmacist having to handle it. The irradiation time depends on a number of things, the probability of activating the target atoms, the energy of the particles, and the number of particles that are striking the target at any given time. The commercial cyclotrons typically start producing F18 at midnight, the night prior to shipping out the material to hospitals. The PET radiopharmaceuticals have high energies, and so they're produced in large quantities also. The production must take place in lead-shielded hot cells with automated systems called synthesis modules. Those are new terms for you as you're learning PET, but essentially that hot cell is where all the radionuclides is stored while it's being used, and it is surrounded by lead. It's called a hot cell mostly because it's so radioactive. There's a lot of activity present. And then because it is so radioactive, the tagging that occurs to make the radiopharmaceutical is done in automated machines or automated systems that are called synthesis modules. And these are controlled by computers to perform the needed chemistry and attach the radioactive atoms to the radiopharmaceutical compound. This saves the radiopharmacist from having to handle very high amounts of radiation. With F18 labeling, this is accomplished through a reaction called nucleophilic substitution. The chemical reaction in which each electron-rich group of atoms changes place in a module with a positively charged atom. The substitution reaction allows the reactive F18 to be placed in a molecule at a specific location to produce the desired compound. So you're basically replacing the fluoride deoxyglucose, or you're basically replacing that with a radioactive form of the fluorine. Synthesis will take about 30 minutes, and the percent yield conversion of F18 to FDG is about 50 to 80%. And the final product is F18 FDG, also called deoxyfluoroglucose or fluorodeoxyglucose. Quality control must be maintained prior to patient administration. F18 FDG must have not less than 90% or more than 110% of the labeled amount as expressed in millicuries per milliliter at the time of calibration. It also must be carrier free. Carrier free means it's not carrying any other junk with it, any other chemicals, toxins, radionuclides. It needs to be pure. And this is provided in a single use or multi-use container. Now, the USP and the FDA regulate regulate the production of FDG, and the regulations required for the labels include the time and date of calibration, the amount of FDG as expressed in megabecquerels or millicuries per milliliter at the time it was calibrated, the expiration time and the date, the name and quantity of any preservative or stabilizing agent that was used. The radioactive decay calculations should use a half-life of 109.7 minutes, and it must have a statement sticker on it that says caution radioactive material, and then they also must have a statement on it that says not to use it if it's cloudy or it contains any particulate matter. Now, carbon-11, nitrogen-13, and oxygen-15 are biologic compounds that are used to show biologic function. So for these, no additional radio labeling occurs. They are used in their pure form straight out of the cyclotron. Copper-64 is a little bit different. It requires radio labeling. So it's radio labeled with chelation to peptides, antibodies, or nanoparticles. And the picture that's here is the TechNet. That's a brand name for copper-68 dotatate, which is used for neuroendocrine tumor imaging. So for F18 as the example, the test that's done, there are several different tests that are done. The first one is appearance. It must just be colorless, clear, and free of particles, not cloudy. The radiopharmaceutical or radionuclide identity, it needs to have a half-life between 105 and 115 minutes, so we know that it's F18. The radiochemical identity is done by assessing the thin layer chromatography, and then bacterial endotoxin test is not done on every single sample because it takes a long time for those results to come back. But that's the BET, or the bacterial endotoxin test, and it must contain not more than 175 USP endotoxin units, which are essentially a made-up unit by the USP of how many bacteria or how many endotoxins are allowed per volume. The pH needs to be about 0.45 or 4.5 to 7.5. The closest that it is to human pH, the better. And then chemical purity is measured one of two ways, either the Cryptofix 222 or CIDG. And these are the testing requirements depend on the synthesis module that's used. For the Cryptofix, it must be less than 50 milligrams per milliliter per batch tested. And for the CIDG, the content is not more than 1 milligram per administered dose. So radiochemical purity, the radioactivity of the FDG cannot be less than 90% tagged. So radiochemical purity is just saying that It has to be FDG. You don't want a lot of free F18 in there. So it must be at least 90% tagged, and this is done using thin layer chromatography testing. Radionuclide purity to make sure that it is F18 and that there are not any other radionuclides present. And the stable gamma ray spectrometer is used for that to make sure that it really is F18. And then any residual solvents, you can't have, you must have less than 0.04% acetonitrile and 0.5% ethanol. So those are the basics of positron decay and the production of radionuclides for PET CT imaging.